Welcome to One Chemistry. We are seeing organic chemistry concepts. In this video, we are going to see benzene reaction. It includes mechanism and solve 21 examples. We'll see very detailed way. Stay tuned. What is inside this video? First, we will see what is benzene. Then we will see synthesis of it. We are going to see 11 methods and reaction. The reactions involve nucleophilic substitution and Diels-Alder reaction. Then very important part, 21 fully solved examples from various examinations. First, let us see what is benzene and the basics involved in it. Benzene is normally derived from benzene. It's a benzene with one triple bond. It can be imagined with perpendicular p orbital or it can imagine like radical. Both way you can explain the benzene, but best way is draw triple bond and involve in the reaction. Since p orbital is perpendicular, it don't participate in the delocalization, so it is aromatic. It is unstable or you can say reactive because triple bond need 180 degree, here only 60 degree, so it is very reactive. It is an electrophile because of incomplete octet. It will undergo elimination addition mechanism. Basically it is called SN2AR mechanism or simply SNAR mechanism. Then we will see how we can prepare benzene. 11 synthetic methods known. We will see one by one. The first method involves anthralinic acid, benzene with amine and acid. You are using amyl nitrate. Basically, you are converting amine into diazonium salt. Diazonium salt contains N2. It's a very good leaving group. And acid also can leave because CO2 also leaving group. Both N2 and CO2 is the good leaving group. It leaves you form benzene. So whenever you see anthralinic acid, you imagine benzene formation. Then the next synthetic method, chlorobenzene with butyl lithium. Butyl lithium is the strong base. It abstracts the proton. You have anion formation. Then the anion push the chlorine out. You have benzene formation. Basically, you have Hessian elimination. Double bond become triple bond there. It is like dehydrohalogenation. Finally, you have benzene. Then the next synthetic method, you have benzene fused with peroxide. It contains two carbonyl and continuous oxygen. You are using the light. Continuous oxygen is called peroxide. Basically, it has lone pair, repulsion is very high, the bond is weak. If you use light, light promotes the radical formation, so radical forms. But the radical is very reactive, it promotes the leaving of CO2. So it has two possible CO2 elimination. CO2 eliminates, you have benzene formation. So peroxide push the CO2 out, you have benzene at the final step. Then next synthetic method, you have benzene which is attached with heterocyclic sulfur dioxide and azo bond. You are heating it up. Heating at high temperature promote the decomposition reaction. Decomposition means broken into pieces. Here there are two gases formation is possible. One is N2 and SO2. When you heat it up, it eliminates two leaving group from adjacent carbon, leading to the benzene formation. So basically we are playing with leaving group to get the benzene. Then the next synthetic method, you have benzene attached with three different continuous nitrogen. You have fused system, benzene and heterocyclic. Heterocyclic contains three nitrogen and amine. You are reacting with nitrous acid. Nitrous acid converts NH2 into diazonium salt. Basically, we are promoting N2 elimination. N2 bond is strong and it is a gas. So 2N2 leave from two different carbon leads to the benzene. So you start from amine N with benzene through the elimination of N2. Then the next example, you have fluorobromobenzene reacting with magnesium. Chances of Grignard reagent formation, which will form bromine or fluorine. Bromine bond is weaker when compared to fluorine, so it forms Grignard reagent. Basically, it's a chemoselectivity. We are choosing between bromine and fluorine. Magnesium form Grignard reagent. Basically, it's a nucleophile. Since there is no possible quenching pathway, fluorine eliminates, you have benzene formation. Fluorine rarely acts as a leaving group. Due to the instability, here it leaves, you have benzene formation. Then the next synthetic method, you have dichlorobenzene, you are reacting with magnesium. It absorbs 2 chlorine, you have benzene formation. Basically, magnesium capture 2 chlorine, form a salt. It leads to the benzene formation. It's a simple straightforward reaction. You can easily convert it into benzene. Then the next example, you have benzene attached with iodide and mercuric iodide. Both are in adjacent carbon. You are doing photolysis. Photolysis remove mercuric iodide and iodine, leave us HgI2, which leads to the formation of benzene. So you have benzene formation from unexpected salt, which is similar to the Grignard reagent. Mostly you guess the leaving group and possibility of assisting group, you will get the benzene. Then the next example, you have benzene with very good leaving group, which is triplet. Triplet stabilize itself, leave quickly. If you use LDA, LDA is the strong base, lithium diisopropylamide. So if you use LDA, LDA abstract the hydrogen, you have anion. Anion is nearby leaving group, mean you have benzene formation. Then the next synthetic method, benzene attached with 4-member diketone. You are using the LDA. Diketone is very reactive one because carbonyl bonds are there, which is sp2 hybridized carbon. Here bond angle demand 90 degree. It is highly unstable, act as a leaving group. So 2CO can be easily eliminated. If you use high temperature with strong base, CO eliminates, you have benzene formation. So to form a benzene, you take the unstable molecule, convert into stable. So you utilize the conversion, form a benzene. Then the next synthetic method, you have benzene with 1,2 position trimethylsilyl group and triplet. You are using TBAF. TBAF means tetra N-butyl ammonium fluoride. Triplet is the good leaving group. Obviously, if you are using fluoride compound mean trimethylsilyl eliminates, you have the nucleophile. Finally, you have triplet elimination. So, 2 elimination in the adjacent carbon leads to the benzene formation. Basically, 2 leaving group with a catalyst, you are converting into benzene. Now let us see benzene reaction. Basically 2 different types. Let us see the first set of reaction. First type will be nucleophilic attack on the benzene. Nucleophile can attack anywhere, but intermediate has to be stabilized. In the case of electron withdrawing group, nucleophile attack 3rd position. In the case of electron donating group, anion electron donating group repel each other, so attack will happen on 2nd position. Basically regioselectivity between 2 positions. Electron withdrawing means 3rd position attack, electron donating means 2nd position attack. Then the next type of reaction, normally diene and dienophile involved in the Diels-Alder reaction. Benzene is the electrophile, it can act as a dienophile. So diene-dienophile reaction means you have the fusion. Finally 4 plus 2 cycloaddition product. So benzene has 2 possible reactions. Then we are going to solve 21 problems. Why so many problems means different problems give different set of perspective. It helps you to understand the concept much better. So problems are best way to learn. Let us see the first example. Here you have trifluorotoluene with chlorine at the second position, ortho substitution. You are reacting with sodamide and ammonia. You should find what will be the final product. Here you are using the sodamide. Sodamide is the strong base. Strong base subtract the proton, which leads to the anion formation. Anion is unstable. Nearby group chlorine is there. Chlorine is the good leaving group. So anion migrates. You have benzyne formation. Then the amine as a nucleophile attacks. Where it will attack? Ortho or meta. Both possibilities are there, but only in the meta position leads to the anion near CF3. CF3 contains 3 fluorine, highly electron withdrawing in nature. It can stabilize the anion. So meta substitution leads to the stable intermediate. Then hydrogen quench the anion. Finally, you have 1,3 product. The concept you outline here is anion stability dictate the final product in the Benzyne reaction. Then the next example, you have pyridine with third position chlorine. You are reacting with sodamide and ammonia. You should find what will be the final product. Here the problem in the blind side, you should redraw the molecule with hydrogen and nitrogen lone pair. Then possibility of amide proton abstraction. Strong base abstract the proton, but you have two possibilities, A proton and B proton. Both possibilities if you analyze, B proton leads to the anion near lone pair, which leads to the repulsion because lone pair also electron, anion also electron. So repulsion leads to the unstable product, so it is minor. If you look at the A, it is reasonably stable. Anion forms. Anion has to be quenched, so chlorine leaves. You have benzyne formation. Benzene is there. Next amine attacks. Here amine can attack either way because there is no selectivity here. Final products with equal possibility. The concept you outline here is in pyridine, proton abstraction never happened in the nearby carbon. Then the next example, you have benzene with attached dicarbonyl with peroxide bond. You are using the light, sodamide and ammonia. You should find what will be the final product. The compound contains continuous oxygen, which is called peroxide. Peroxide has two lone pair. The repulsion is high because lone pair repulsion is highest. So it repels, the bond is weak. Moreover, you are using the light. Light promotes the radical formation. So two controlling factor, repulsion as well as light, leads to the radical formation. Radical can be quenched as benzyne. 2CO2 eliminates, you have benzyne there. Then sodamide attacks, you have finally aniline there. The concept you outline here is whenever you have peroxide bond, it is unstable, promote the radical formation. Then the next example, you have benzene with two halogens, fluorine and bromine. You are reacting with furan and magnesium. You should find what will be the final product. Here you are using the magnesium. Magnesium can form Grignard reagent, but when compare the bond length, bromine is weaker, it forms quickly. On the contrary, fluorine is stronger, it never forms Grignard reagent. So magnesium promotes the anion. Anion has to be quenched. It will be quenched as the benzyne. So you start from dihalogen, you end up with benzyne. Benzene is the dienophile. It reacts with diene, furan diene. It reacts, you have 4 plus 2 cycloaddition. The concept you outline here is dihalogen can be removed by magnesium through Grignard reagent formation. Then the next example, you have bromobenzene. You are reacting with sodium tertiary butoxide. You should find what will be the final product. Tertiary butoxide you are using. Tertiary butoxide is the base. It obstructs the proton, leads to the anion formation. The anion is unstable. It has to be quenched. Bromine is the good leaving group. So anion forms a triple bond. The triple bond leads to the benzyne formation. Then butoxide attacks, you have anion formation. Then anion bonds with H plus, you have the final product. The concept you outline here is whenever you have halobenzene with strong base, normally you end up with benzyne and Benzyne mechanism. Then the next example, you have cyclohexadiene, you are reacting with benzene and heating it up. You should find what will be the final product. The reaction is straightforward. You have diene and dienophile situation. Benzene can act as a dienophile because it is already electrophile, so it can easily act as a dienophile. So 4 plus 2 cyclohexane is possible, which is called Diels-Alder reaction. So final fused product happen. Here I given numbers for quick and easy understanding. Here 1, 2, 3, 4 carbon formed with fusion. 5 is co-acid bridge. The concept you outline here is benzene can act as a dienophile. It can undergo Diels-Alder reaction. Then the next example, you have chlorobenzene. You are reacting with sodamide and furan. You should find what will be the final product. Here you have chlorobenzene. You are using the strong base. Strong base abstract the proton, which leads to the anion. Anion has to be quenched. Since there is no leaving group, fluorine should leave to form benzene. You heard it correct. Fluorine is the leaving group because charge quenching is the highest priority. Benzene forms. Benzene can act as a dienophile. Diene you are using, it leads to the 4 plus 2 cycloaddition. The concept you outline here is charge quenching is the highest priority. To quench the charge, fluorine can act as the leaving group. Then the next example, you have chlorobenzene. You are reacting with butyl lithium and cyclopentadienone and heating it up. You should find what will be the final product. Here you have chlorobenzene. You are using the butyl lithium. Butyl lithium is the strong base. It abstracts the proton. The abstraction leads to the nucleophile, the anion. The anion has to be quenched. So chlorine leaves. You have benzene formation. Benzene, as we discussed already, it's a dienophile. It can react with diene. It forms 4 plus 2 cycloaddition. Finally, CO will be eliminated. You have naphthalene there. Here, whole reaction promoted by the ring strength as well as aromaticity. The concept you outline here is benzene can act as the dienophile. Then the next example, you have 2-chlorotoluene. You are reacting with sodamide and ammonia. You should find what will be the final product. Here you are using the sodamide. As we discussed, it's a strong base. It abstracts the proton, leads to the anion formation. Anion has to be quenched. Chlorine is the good leaving group. It leaves, it forms benzene formation. Then the nucleophile attack, which is NH2. It can form two ways, but both ways are equally possible because CH3 is less bulkier and less influential because CH3 is hyperconjugative, not inductive or mesomeric. It is also less steric. So CH3 gives 50-50 chance for the amine formation. So both ortho and meta attack is possible. You have the final product with the mixture. The concept you outline here is in toluene, methyl group don't influence the final product formation. Then the next example, you have chlorobenzene. You are reacting with butyl lithium and anthracene. You should find what will be the final product. Here you have chlorobenzene. Butyl lithium is very strong base. It abstracts the proton. Proton forms nucleophile. The charge has to be quenched. It quenched by chlorine elimination form benzene. Benzene can act as a dienophile and you are using the anthracene. The middle ring of anthracene can act as a diene. Why? Because of annihilation effect. Annihilation effect means individual aromaticity of the benzene ring. Among the three rings, A and C individually aromatic, B is weakly aromatic. If you write imaginary structure, you can identify easily. Middle ring is less aromatic, so it will undergo Diels-Alder reaction. 4 plus 2 cycloaddition is possible, so it forms like bridged benzene. The concept you outlined here is benzene can act as a dienophile. It attacks the anthracene, form the unusual bridged product. Then the next example, you have orthochloroanisole reacting with sodamide and ammonia. You should find what will be the final product. Here sodamide you are using. Sodamide is the strong base. It abstracts the proton. You have the nucleophile. The negative charge is there. Negative charge has to be quenched. It will be quenched as the benzene. Chlorine elimination leads to the triple bond formation. Benzene forms. Then the nucleophile attack. Where it will attack? Ortho or meta. If you look at it, both are equally possible. But ortho position attack is weaker. Why? Because of steric effect of methyl. So meta substitution is possible. Stable anion forms. You have proton abstraction. Finally, you have meta substituted product. The concept you outlined here is O-methyl group will behave like a electron withdrawing group, promote the meta substitution. Then the next example, you have anthralinic acid reacting with amyl nitrate and furan, heating it up. You should find what will be the final product. Here furan given with confusion like solvent. Here it is a reactant. Starting material is anthralinic acid. You are reacting with amyl nitrate. It forms diazonium salt. You have two possible leaving groups, N2 and CO2. So hydrogen elimination leads to the two gas elimination, which is N2 and CO2. Two leaving group in the adjacent carbon leads to the benzene formation. So benzene is there. It can act as a dienophile. You are reacting with diene. So diene and dienophile mean Diels-Alder reaction. 4 plus 2 cycloaddition happen. You have the final product. The concept you outlined here is whenever you have two adjacent leaving group, you should expect Benzyne mechanism. Then the next example, you have benzene with heterocyclic nitrogen which have continuous 4 nitrogen bond reacting with nitrous acid, sodamide and ammonia. You should find what will be the final product. Here continuous nitrogen you are using. The nitrogen containing compounds are very weak, decompose rapidly, so it is highly unstable. In the first step, amine group is there. We are using nitrous acid. It's a conversion of amine into diazonium salt. Basically, you are promoting the N2 elimination. 4N group means 2N2 elimination. N2 contains strong triple bond, form quickly, make it as a very good leaving group. So N2 eliminates, you have benzene. Then sodamide attacks, you have the final product which is aniline. The concept you outlined here is heterocyclic compounds with many nitrogen is unstable. You should expect benzene formation if it is present in the adjacent position. Then the next example, you have benzene with nitrogen and sulfur dioxide. You are heating it up and you are using sodamide and ammonia. You should find what will be the final product. Here you are having specific heterocycle which contain two possible gas elimination, which is N2 and SO2. You are heating at high temperature which promote decomposition reaction. N2 and SO2 leave from the adjacent carbon. You have benzyne formation. Benzene forms, you have sodamide attacks, you have aniline there. The concept you have to learn here is whenever two leaving group present in the adjacent carbon, that is nearby carbon meet, you should exploit Benzyne mechanism. Then the next example, you have toluene, metaposition bromine, another metaposition long chain secondary amine reacting with phenyl lithium. You should find what will be the final product. Here you are using the butyl lithium. Butyl lithium is the strong base. It abstracts the proton. Here two sets of protons are there. Proton eliminates. You have anion. Then the anion quenched as the benzyne there. So benzyne is unstable. It's a electrophile. So amine is the nucleophile. So attack is possible. It can attack two positions. Which one is possible? The attack leads to the stable 6-member ring. 7-member ring also possible, but impossible ring size leads to the unstable compound. 6-member, if you read down nicely, you have fused nitrogen, which is reduced pyridine compound. The concept you have to learn here is nucleophile can be internal. If benzyne form, it will attack very quickly. So it's a intra reaction promoted by the internal attack. Then the next example, you have benzyne reacting with hexadiene, heating it up. You should find what will be the final product. Here you have benzyne. Benzyne can act as a dienophile because it's a electrophile and diene is there. Diene should be electron rich. It is already rich by methyl group. You are heating it up. So 4 plus 2 cycloaddition is possible. It is called Diels-Alder reaction. It forms fusion product. The important here is the reaction happen in the same plane, or you can say syn addition. So methyl groups are syn to each other. Benzyne reaction involves syn addition with Diels-Alder reaction. Then the next example, you have para-chlorotoluene, which is with trifluoro substitution. You are reacting with sodamide and ammonia. You should find what will be the final product. Here sodamide you are using, it's a strong base. The strong base abstracts the proton. You have the anion formation. Anion has to be quenched. It will be quenched as the benzyne. So chlorine eliminates, benzyne formed. Then the nucleophile attacks. Nucleophile is amine. It can either attack meta or para, but meta position leads to the anion near to the chlorotoluene, near to the fluorine. So it's an electron withdrawing group. Even though it has hyperconjugation, electron withdrawing ability dominated. You have the final product with para substitution. Then the anion quenched, you have hydrogen there. The concept you have to learn here is anion stability dictate the benzene reaction pathway. Then the next example, you have benzene, which is phenol containing para-chlorobenzene. You are reacting with sodamide and ammonia. You should find what will be the final product. Here sodamide you are using. Sodamide abstract the proton, leads to the anion formation. The anion is unstable. It should form benzyne. Chlorine eliminates, benzyne forms. But the interesting fact here is base abstract both the proton, which is from phenol, as well as metaproton. So it can involve the delocalization, stabilize the benzyne there. So bond delocalizes. You have negative charge in the 3 different carbon. So only meta position is electron deficient. So amide is the nucleophile. Same charges repel each other. So only attack happen on the meta. So final product is meta substituted. Proton donation leads to the meta amino phenol. The concept you outline here is cation stability dictate the electron density, which leads to the meta substitution. Then the next example. Here you have benzene with isopropyl group and chlorine reacting with phenyl lithium and ammonia. You should find what will be the final product. Here you might confuse, there may be a steric effect, but tetrahedral bond, all bonds are equal, so it can go away, hydrogen come as a friend because single bond can rotate, steric effect is pushed away, you have chlorine there, you have possibility of Benzyne formation, so proton abstraction, you have anion formation, the anion promote the chlorine elimination, leads to the Benzine. Then phenyl lithium you are using. Phenyl lithium promote the pH minus, which is nucleophile, which can attack either position, but it attacks only meta because anion stabilized by hyperconjugation. So due to the steric effect, phenyl attacks meta, anion formed near the isopropyl group. You have the major intermediate. Then the anion quenched with proton. You have the final product. The concept you outline here is steric effect can dictate the Benzyne mechanism. Then the next example, you have benzene with 3 substitutions, 2 nitro group and chlorine, all are in meta relation. You are reacting with sodium methoxide, hydrogen iodide and heating it up. You should find what will be the final product. Here you are having chlorine nearby hydrogen. So obviously base obstruct the proton. You have anion formation. The anion promote the chlorine elimination. You have benzene. Next step is interesting where the methoxide attacks. Since the structure is symmetrical, you have the anion formed near nitro. Nitro also stabilize the anion because it is electron withdrawing group. Next step you are adding hydrogen iodide. Hydrogen iodide where it attacks, it can attack in the either possible way. It can break the bond A or B pathway. A pathway is impossible because it's a sp2 carbon, bond length is less. So only P break is possible. You end up with phenol. The concept you outline here is in Benzyne mechanism, always stable intermediate form, the substitution happen away from the electron withdrawing group. Then the final example, you have chlorobromobenzene reacting with magnesium and ether. You should find what will be the final product. Here you have magnesium. It can form Grignard reagent where it will form with bromine or chlorine. Bromine bond is little bit loose or weak. So magnesium form with bromine. It's a chemoselectivity. Bond length decides it. It form nucleophile. It will quench as the benzene because chlorine is the good leaving group. It leaves, form the triple bond, leads to the benzene formation. Since there is no further reaction, benzene is highly unstable. It combines, form the dimer there. Basically end up with dimerization. The concept you outline here is benzene is the intermediate. It is highly unstable. If you leave it without stabilization or reaction, it will dimerize. Dimerization reaction will happen. Then let us conclude by the summary. We learned benzene is the electrophile and very reactive. It is highly unstable. Why? Because it has triple bond in the benzene architecture. It cannot accommodate 180 degree. That's why it's reactive. Benzene can undergo two sets of reaction. First with substitution. Substitution can be electron withdrawing group or donating group. Electron withdrawing group can stabilize the anion. So substitution happen at the third step. On the contrary, electron donating group destabilize the anion. So substitution happen at the second step. So second type of reaction is benzyne can act as a dienophile. So dienophile situation leads to the Diels-Alder reaction. Then one important point is O-methyl behave like electron withdrawing group. The reason is due to steric effect, but to memorize you should know OMe always promote the third position attack.